The day, it's day 8, right?
Oh, so.
Ow. Fucking hand cramps up from opening the bin. Alright, it's a new pin, it's stuck on tight. We are doing lunch of day 8, we're gonna do some prep work. For 9.3. And it's effectively part of 9.4 too. Because they're both on graphing functions. Okay, I don't want to use that black pen yet. So we will go over this again in the main course, but I think if I do it a couple times with you, the better chance it's locked in. We kind of have, oh, let me write that one in. We kind of have like 6 basic graphs. That model actually a lot of information. We got more, but we're not going to do the exponential and logs till later on. We have f of x equals x. And that is quite literally just a diagonal line. It's a perfect diagonal line. Like when x goes up 1, y goes up 1. So the 0.11. This has the name identity function, which I won't repeat again, well, other than the next class, because I don't see how that's helpful for students. But if you're gonna be a math major, it's good to know the lingo. Then we have f of x equals x squared. Just make a little table real quick. When x is plus or minus 1, y is 1. When x is plus or minus 2, y is 4. Whatever's here is squared over here. You can see that if you plug it in the function. This is called the squaring function. Let's put some hash marks on here. And we have 0, 0 in the middle. If I go left, right, left 1 or right 1, I go up 1. And if I go left or right 2, I go up 4. And this is, wow, my hand's all wiggling. This should look like it's curved, it's rounded down here. It's not a crisp point. This is called the squaring function. I think the identity is easy to remember, it's the fucking diagonal. As long as you know 1, 2, and 3 squared, f of x equals x squared is really easy too. You just go left or right and you go up the same amount. And so previously we were talking about domain and range, let's list those. Domain here is all real numbers. So we could write it as negative infinity to infinity. I could put that on both for the identity function. Another way of saying this, all real numbers, we have a symbol for it. It's a capital R with a double vertical line. That's math jargon for all real numbers. You don't see the double vertical line on any other use for a letter, so like you know how they do with the P for paragraph? You know exactly when you see that what that is, even if you haven't taken English for a while. Like that doesn't have any other purpose. We look at squaring function. The domain is all real numbers, but the range is not. Remember, range is the y values. So range is, domain is the x values, range is the y values. And the y values are the vertical part. So we don't have any in the negatives. Y, the graph actually starts hitting when y equals 0. So the range starts at 0 and goes up to infinity.
Kind of like a flashlight in the dark, right?
The parabola kind of looks like a flashlight. In fact, headlamps on cars and flashlights are modeled using parabolas. When we go over parabolas more later on, it won't be this month or this week. When we hit it more, I'll actually show you the how the flashlights and stuff work. And so you might like that. You'd be like, oh shit, it's math in real life. My car has a parabola. Who would have guessed? That's the other name for this thing. This shape, the shape is called parabola. Parabola, but it's not pronounced parabola. It's pronounced parabola. Ready for some more?
Yes.
This is not the funnest shit you've ever done. So we did x to the first power, we did x to the second power. The last one we'll do with the exponent that's a whole number is the cubing function. So since it's cubed, the squares turn every y positive. Cubing doesn't. A negative will stay negative. So 0 still goes to 0, 0. But positive 1 goes to positive 1, and negative 1 goes to negative 1. A short way of saying that is plus or minus 1, and then plus or minus 1. So match up the signs. That's a short way of saying that. If I do the 2 plus or minus 2, that same idea, I get plus or minus 8. Because 2 cubed is 8. This one is a much more straight up and down graph. It kind of goes kind of tall. Okay. So we got 0, 0. And we got +1 for both and -1 for both. And these are actually in a straight line right now, but the fact that 2 goes all the way up to 8 and -2 goes all the way down to -8 means it is not a straight line. So it kind of looks like a really steep parabola that changes direction. Not quite. We don't have a fun name for this. Like the other one was line and parabola, this is just a curve.
So
And specifically, most people would just call it the x cubed graph. Because it's recognizable. Domain and range here. So remember, domain is the x values. And if I start on the left side of the graph, I hit the graph immediately, even though it's kind of way down, it's a long ways away. This thing, if I keep going far enough out, I'll eventually find an x that's on the graph. So it's again, -infinity to infinity. As long as there's even a slight angle when you have a graph with an arrow, it means it's eventually going to hit all the x's that way. Same thing in the positive direction. The range also does this. The range is the y values. For this, we go up and down, and we're going from -infinity all the way up to positive. So I'll do the other symbol, the all real numbers. You having a special day?
yeah.
So you're trying to get through that door and look like a challenge.
Yes. We went to the action today.
When we left campus on fucking Tuesday, that fucking traffic light was a clusterfuck in every direction.
You should see the coming towards this way, like going towards LA.
I bet.
The freeway is so packed.
I bet the freeway's fucked.
Destroyed.
And I'm like, why is the traffic backed up so fucking far? I even tried to change directions, go down a back road to get on like a different. Moaning as fuck all the way down towards as I could say for a while. Alright, next graph. Let's do square root of x. Now, you could be a psychopath and stick in 0, 1, and 2. But I don't know the square root of 2, square root of 3 very well. It's better to pick numbers here that are perfect squares. Like start with y equals 0, 1, and 2, and the square values are 0, 1, and 4. That way, when I take the square root of 4, I get the 2. And this keeps going. 9, 3, 16, 4. Wow. That's just fucking terrible. Let's try to straighten that out a little bit. I felt okay doing that because notice that none of these numbers are negative. If I try to put in a negative x here, my calculator is going to say fuck you. I'll say error. But if it could say fuck you, it would definitely say fuck you. I'm waiting for ChatGPT to figure out foul language. That'd be great. I want my AI going, are you really that dumb? You fucking dumb shit, it's this. That'd be great. They'll figure it out one of these days.
It'll be like a setting, it'll be like a freer chat GPT, opinionated chat GPT or something.
Right.
That's like, what the heck?
So it starts at 0, 0. And we have 1, 1. And then we have 4, 2. And then I have 9, 3. If we look at the graph of x squared real quick. Let's see. It kind of looks like x squared, but just the top half, sideways. Sideways, I rotate the page. It's like x squared sideways, but only the top half. There's a reason for that. Square root of x and x squared are inverse functions. And we'll go over inverse functions another day. But there is a reason why they look similar. So the domain and range here, remember domain is x and range is y. If we're looking at the domain, we're looking at the x values, there's no negative x values. The graph starts when x equals 0. And it keeps going to infinity. And the same happens with the range. We did this design before. This was called interval notation. We did this notation back in the inequality section. This effectively corresponds to the inequality x is greater than or equal to 0 and y is greater than or equal to 0. So that's a little tie into some of that inequality stuff we did earlier. Ready for more?
Yes.
Might I have another? Is that it? Did that do it for you, Lauren? To bring up some Christmas shit for you? Fucking, is that Oliver Twist? What?
I just see the kids' face.
Okay, it's great.
That's fucking off. I'm glad. Glad you're finding some joy in this. That's why I do shit like this. Believe it or not. I try to be different than the other teachers by being more me than. This is the absolute value function. This kind of combines what x squared did, where everything just stays positive, but also combines the line. So plus or minus 1 just leads to 1, plus or minus 2 just leads to 2. The straight line at an angle is fucking killing me. Oh, we have a guest. Hey, Roberto. Like, fuck that, I ain't doing that drive. This place looks like shit. Okay, this one actually does, this is a nice crisp point. It's a corner. All the other drafts have been rounded. This one is a corner. In fact, if we just look at the right side of the graph, this looks like y equals x. And when we look at the left side of the graph, this looks like y equals negative x. I'm not doing 9.5 today, but 9.5, I'm gonna make the video tomorrow morning and post it. It's on piecewise functions. Absolute value is a piecewise function. They say piecewise, but it comes in pieces. It has different pieces for different parts of the domain. How we would write this as a piecewise function. We get it's a curly brace. And we say, what we say is what the y value is. So for like less than 0, if x is less than 0. Fuck, I can even say less than or equal to 0 for this. F of x equals negative x. And if x is greater than 0, it equals x. That's how we note piecewise functions. It's where the graphs look like different shit on different parts. That's all.
So if there's a piecewise function. And it could be like that shape, it could be like y equals x on one side and then be the root x on the other side.
Yeah.
Yeah, just both can work.
Yeah. It doesn't need to just be 2 parts either. I can have like fucking 10 parts. I can have as many parts as I want. Well, as are appropriate for whatever the application is.
Right.
Anything else is just fucking doing fun shit with math, and no one likes doing too much fun shit with math. A certain dose of fun is all right. But just having like a fucking piecewise function with 10 parts is someone's getting slapped. And I don't want that someone to be me, so we're not doing it. What's the other one? The reciprocal function. Oh, let's talk about domain and range. Before I go on. We can see that the domain, all x values work. No matter what x I plug in, I'm gonna get a y. So the domain is all real numbers. The range has a restriction though. Range doesn't go negative. So it's 0 to infinity. You guys ready for more?
Yes.
He's all eager. Says yes, please. More, please. Finally, we have the reciprocal function. Reciprocal. F of x equals 1 over x. So I can make a little table here. Let's do like -3, -2, -1, 0, 1, 2, 3. I want to kind of show you what happens. When I stick in -3, I get 1 over -3, so -1/3. If I stick in -2 in the function, this is like doing f of -2. Let's tie this into our lecture from Tuesday. I have 1 over -2, so -1/2. If I stick in -1, I get -1. Here I stick in 0, I get 1 over 0, which is undefined. If I stick in 1, I get +1. This kind of does the same thing as the negatives going the other direction.
Yeah, I was just about to say that. They match.
So like, let's draw a graph here. Maybe kind of big. Just doing 1/3 is gonna take a little room and make that y shape look a little bit bigger. So right now I got -3 and -1/3, which is kind of like that. And -2 and -1/2 is like that. And -1 is -1. I don't know what's going on around 0, but we had 1, 1, 2, 1/2, and 3, 1/3. So like, I want to be able to fill in this graph a little bit better. What I'm gonna do is I'm gonna extend this list. And I saw that no matter what I plugged in for the negative or positive, they kind of look the same. So I'll just look at, like, maybe we'll do the halfway points. Like if I stick in plus or minus 1/2, what do I get? Well, the name is called the reciprocal function. The reciprocal function is flip the shit over. So if I did this 1 over 1/2, we could clear fractions. I could do this the good old mathematics way. Multiply this by 2 over 1, 2 over 1. The bottom goes to 1 and the top is 2. Which is effectively just flipping the 1/2 over. So this will be plus or minus 2. And if I did the same thing with 1/3, I get plus or minus 3.
Is there an instance where doing that multiplication of fractions thing doesn't work? Is there like any barrier for using that?
If there's a 0 showing up somewhere.
So like if there's a potential for it to.
Right.
But other than that, we can kind of do what you just did there and multiply the bottom number.
Right. If there's no 0, like the only time you would do this mathematically is. Unless there's a shitty rational equation they're called. But actually doing a calculation, yes, it's literally just flip it over.
That's what I was taught, and I was like,
So I got plus or minus 1/2 gives me plus or minus 2, and plus or minus 1/3 is plus or minus 3. So it looks like our graph does shit like this. We know it doesn't hit zero because zero is undefined. So I can't have x equals 0. It's gotta be a nice little curve, but it looks like it gets really, really close to that y-axis. It looks like it gets really, really close to that x-axis. Because these fractions will keep getting smaller. But there's no real way to get a y equals 0 here, is there? No, I would need a 0 on top, and I have a 1 on top. There's no way to get a 0 on top. So there's no like y value here that's equal 0. So that's the graph of the reciprocal graph. When it does shit like this, where it starts going but never crossing a line, we can put like a dashed line there. We'll be doing this more later, but since it's a support course, we'll hit you with it now. Dash line there. And the dashed lines are called, does anyone remember what they're called?
Asymptotes.
Asymptotes.
And the asymptotes represent like it's getting close to the line, but it's never touching it.
It's getting close to the line, but it never crosses it
So it's kind of the same.
or touches it, yeah.
It's kind of the same thing as the open dot, like on the other graphic we do here. Like when it's just one axis, when it's just one measurement, we have like an open dot, which is the less than symbol. Like
Yeah.
X less than 3, at 3 would be an open dot, so it's similar,
It's similar in that there's no value there,
but it's not the same.
but it's not the same thing. On during break, I'll show you a piecewise function that has that.
So they're not the same, it's not. the
No.
same thing.
They're both not, they don't have a point there, but like. You can have a line that just has a hole in it. And it doesn't have an asymptote. Or show asymptotic is the description part, asymptotic behavior near it. This one does. Alright, those are our basic functions. We'll learn to modify each of them today. Lauren's enjoying herself, we can give her some more time. Sarah looks bored. What?
You go to AEC, I was gonna say they were talking about the smart pen at AEC. I didn't get it, but.
A smart pad? What's
pen.
smart about it? Oh, smart pen.
Oh, it's an Apple. Oh, sorry. I was gonna say they were offering something like that at AEC and they didn't take them up on it, but they're on Apple. That's great.
Huh,
We like the.
my Surface Pro, I got a pin for it and. When I write with it, I wanna write with it at a normal speed. And it does, there's fucking gaps in the writing, they're like the pen does, I'm not lifting the fucking thing up. But it's not recording like, it'll look like I'm fucking running out of ink while I'm writing. Fucking irritating, does that happen on yours? Is it because you write slower or can you write like,
No, you can.
write cursively fast and there's never any gaps? That might be the only advantage to an Apple. That is an Apple, right? Is that what you-
Yeah.
I don't know if it's all Microsoft or it's just me being. I was about to say something that was completely inappropriate for a college teacher to say. Good thing I stopped myself. I say that with my friends. Alright. More shit. We are gonna do a lot of stuff today. Where we look at, well, not a lot, but some. Sticking in negative x into a function. So. I'm gonna write down the 6 basic functions we did today. And we're gonna look at what happens if I stick in negative x. I wrote that wrong, there we go. Before I do that though, maybe I should talk about domain and range on this motherfucker. So domain and range both. The only number it can't be is 0. Which means in interval notation, we do negative infinity to 0 in union with 0 to infinity. That is a terribly boring math way of saying x can't equal 0, y can't equal 0.
The U,
What?
the U is what's saying that.
Having it go up to 0 and then doing union and starting at 0 again. Because these are talking about the regions that numbers work. I go from negative infinity all the way up to 0, but I don't have a bracket. So I don't include 0. So I can go like negative 0.000001. I can't go 0, but then I can go positive 0.000001. So everything up to it, but not including that motherfucker. So there's a little recap of that more of that interval notation we talked about with inequalities. And oftentimes we had more of a gap between them, not just a single number. You want to need that longer? See people still writing. I don't want to get crazy. All right. So when you're trying these for negative x, what you should do is take, like, this is a function. I'm going to stick in negative x. Just the way it shows. I'm replacing just the x with negative x. So here, this is negative x squared. This is like that, and this is negative x cubed with the negative on the inside. Square root of negative x. Absolute value of negative x. And 1 over square root, or not square root, 1 over parentheses negative x. This red pen's dying today. I can see it fading. Last sparks of existence will just fade away. So if we actually calculate what this is, well, that's just negative x. I don't need the parentheses. If I do negative x times negative x, I get positive x squared. And if I do negative x times negative x times negative x again, I get negative x cubed without parentheses. Here I get an imaginary number. We get I square root of x. But this isn't where not what I want to look at. So not part of the pattern. When you have imaginaries, it's a little bit different. Here, the absolute value of negative x is the same thing as the absolute value of positive x. It really is. And this is like negative 1 over x. You ready for more? Where does this matter? What we wanna do is we wanna compare this to the original f of x. So if I stick in negative x, this one looks like, it looks like f of x, but there's a minus sign. So it kind of looks like negative f of x. This one just looks like f of x again. So sticking in negative x didn't change it, right? We're back to the original. This one looks like negative f of x. This is a great way to teach this topic. I'm gonna have to do this in the main course. And this one looks like f of x. And this one looks like negative f of x. Does that make sense? You guys see that? It's a little weird to compare it to the original function. But when we have this happen, and if I can stick in negative x, and I just get back the original, this is called an even function. So there will be questions to say for you to go, is this even or not? And even functions are actually symmetrical about y, the y-axis. So like if we look at f of x equals x squared real quick. The graph looks like this. The y-axis acts like a mirror. It's like a mirror for the line. What happens on one side just mirrors over to the other side. Does that make sense? We call this a reflection across y. We'll be doing this more in 9.4. Reflection across y. And it tends to be very few functions are even functions. As we'll see over the course of the semester, it's really only functions that have just even exponents or absolute value. Absolute value has a special property of being an even function. But usually it's just like x squared, x to the fourth, x to the sixth. Even exponents will have this even function property. But not like x squared plus x. Because then I have a even exponent and I have an odd exponent, and that's like throws it off. And then only a couple of them did that. Then we also saw f of negative x equal negative f of x. We call this an odd function. Where this happens with y equals x to the n and n is even. This occurs when y equals x to the n and n is odd. This provides It's called symmetry about the origin. And it's really fucking hard to visualize. It's like if 0, 0, just the single point was a mirror.
So it kind of means category.
I'll show you how to visualize it. Or how to do it, but like you'll never use, where you'll use symmetry of even functions to like actually speed up graphing. You just do one side and you copy to the other. I don't know that it's really useful for the odd functions. So like we can see that we had x cubed and 1 over x all did this. X, I can't really show it very well. X cubed is too close. Like the way the graph is set up, it's hard to show visually. I'm going to show you how it works on 1 over x. So like, let's look at what symmetry about the origin means on 1 over x. So we'll just do a quick sketch of this. And I hope they did that close enough. So, from the origin, if I go a distance d and hit the graph at a point, I can go the exact opposite direction at distance d and hit the graph also. Does that make sense? And like that might be d1, but the distances don't stay the same, but as long as equal and opposite is the same distance.
Like if it's the slope of one line,
Wait, what?
like it shares the same slope. Like it's a line, like if you're gonna.
Yeah, they need to be, it's like if you did a straight line.
Yeah,
If you drew a straight line through the origin and through your graph, the distance from your graph to the origin should be the same in either direction. Which is crazy. The perfect example of this, which is a little hard to see, is a circle. Because like any direction you go, it happens to work, but then it's like, well, that's just unique to circles. When we do ellipses, I'll show you it on ellipses. Ellipses have that property, this property too. That's near the end of the semester. It looks like it's time to take a pause break. Or actually stop this class